Okay, now we're going to look at freezing point. So we saw with boiling point that adding a solute will increase the boiling point. But now adding a solute to the solvent is going to decrease the freezing point. So on the graph, we have boiling point over there on the right, but on the left, it shows us the freezing point of the solution decreases when we've added a solute. So again, we are going to be able to calculate that. It's a little bit different, but we're going to calculate delta TF, so the freezing point, the change in freezing point, and it's equal to a negative, so that's new. We didn't have that in our boiling point equation. Negative KF, so it's not KB anymore, it's KF. It's the freezing point depression constant, and that's a number we'll look up, times molality times the Van Hoff factor. So the nice thing is, you can, as long as you have the molality, the Van Hoff factor for one, if we've looked up the boiling point of one solution, you can find the freezing point really easily because you already have those numbers. Okay, so that's what we're going to do a new one. Okay, we're going to do a new one for the freezing point. And then once we find the delta TF, we can add that to the freezing point of the pure solvent to find the freezing point of the solution. Okay, so it says find the freezing point of a solution containing 35 grams of iodine, a non-electrolyte, so again, very important, and 315 grams of phenol. Okay, so we're going to take delta TF equal to a negative KF times M times I. Okay, so we're going to go back to that table from your boiling point question and look up the freezing point for our solvent. So iodine is our solute, phenol is our solvent, and so if you look, it says, oh no, I thought the KFs were on there. Just kidding. I'll just give you the KFs. How about that? So looking up the KF for phenol, it is 7.4. Sorry, I thought that was in the table too. So degrees Celsius molality. And it says that iodine is a non-electrolyte, so that just means our Van Hoff factor is going to be at 1. So now we just need to find the molality of our solution. So we have 35 grams. It's molality. We need moles, kilograms. So we have 35 grams of iodine. And we need to find the molar mass. So we're going to divide that by 253.8, which is the molar mass. And that gives me 0.138 moles of iodine. So I have that, 0.138. And now I need kilograms of solvent. It tells us we have 315 grams of phenol. So I just divide that by 1,000 and get 0.315 kilograms of phenol. And that gives me a molality of 0.438. Okay, so that's my missing piece here, 0.438. Okay, and I solve for that. I'm just going to put it down here because I'm out of room. So we're going to take negative 7.4 times 0.438 times 1. And that gives me a negative 3.24 degrees Celsius. So it is going to decrease my freezing point by 3.24 degrees. Okay. So now I want to solve for the freezing point of the solution. And I have to take my delta TF and my freezing point of the pure solvent. Okay, so we take what we solved for. We had negative 3.24 degrees Celsius. We add that to the freezing point of pure phenol. So again, that would be a number that we'd look up, and that is 43 degrees Celsius. And so the freezing point of the solution is now going to be 39.8 degrees. So that's why they put salt on the roads when it's cold and the chance of freezing. We're trying to lower that freezing point of the water. So that's why they salt the roads. Okay, so here's both of the equations together. So make sure when you're looking up KB and KF, you make sure you have the KB if you're doing boiling point, KF if you're doing freezing point. On the test, those numbers will be given. You don't need to memorize those. So we're going to use this equation one more way. We're going to work backwards. Okay, let's say we have an unknown solute. If I have an unknown solute, then I can figure out the mass of my solute, but I don't know the moles because I won't know what the molar mass is. So I can kind of work backwards if I'm given enough information. Okay, so let's look at this problem. It says a solution of unknown non-volatile non-electrolyte, so again, very important, was prepared by dissolving 0.25 grams of the substance in 40 gram of carbon tetrachloride. Boiling point of the resultant solution was 0.357 degrees Celsius higher than that of the pure solvent. So they're actually giving us the delta TB right there, right? It says calculate the molar mass of the solute. Okay, switch over here real fast. Okay, so delta TB we know is equal to KB times M times I. Okay, they gave us delta T, they give us KB, and we know the Van Hoff factor. So we can rearrange this equation to solve for molality because we don't know that number, right? So delta TB divided by KB. I'm just going to leave Van Hoff factor out because it's just one, so it's not going to change anything. Okay, so delta TB, they said, was 0.357, was the change in temperature. KB is given at the bottom there. It is 5.02 degrees Celsius. Whoa. Molality, so degrees Celsius is going to cancel. And we get 0.0711 molal. So there's our molality. And we know molality has moles of solute, kilograms of solvent, right? Well, our goal here is to get to molar mass. And we know molar mass is grams per mole. Well, they told us in the problem that we had 0.25 grams of our unknown substance. So all we really need here is to find how many moles of our substance we have, and then we can divide the two and find molar mass. Okay, we have grams of solvent, so I just changed that to kilograms, and I have molality. So again, I can just rearrange all this to find moles of my unknown. Whoops. Molality divided by kilograms. So my molality is 0.0711 divided by, oh, not divided by, sorry, just kidding, multiply, my bad, multiply by kilograms. Okay, so 0.0711 times 0.04, right? Because all we had to do was take 40, divide by 1,000, that gives us 0.04 kilograms. And we find we have 2.84 10 to the negative 3 moles of our unknown solute. I'll make a negative happen here. There we go. So we have moles of our solute, we have grams of our solute, because it's given in the problem. Now all I have to do is divide the two to find molar mass. Okay, so I take 0.250 grams, that's given in the problem. We just calculated 2.84, 10 to the negative third moles. And we get a molar mass of 88 grams per mole. So again, you only have to do that if you have an unknown solute dissolved into your solvent. And if you have enough information, again, you can just work backwards to find the moles of your solute. And if you're given grams in the problem, you just